Let's talk a little bit about hyperbolic functions, trig functions, and why we need them. They are these guys right here, and they are needed for applications like this. So if you hang what's called a catenary between two poles, all right, you have two poles like this. If you hang a heavy cable in between them, what happens is the cable kind of sags a little more, it's more flat in the bottom than a regular parabola would be. All right, so to take care of this, we need to work with this function and this function here. All right, so there's another application as well. It's the application of waves in deep water and the velocity of the waves in deep water and what their expression can be is using hyperbolic tangent. So there are a lot more applications of this, like the St. Louis arch. I didn't bring it here, but it's in the homework. The St. Louis arch is a hyperbolic cosine function. So how do we start with this? So they're defined like this, but I don't want to define them that way. I want to talk about e to the x first. So let's talk about e to the x. So suppose you have the x and y plane. Remember that e to the x looks like this. So e to the x. And then 1/2 e to the x will look very similar to that. Instead of hitting at 1/2 e to the x hits at 1/2. So 1/2 e to the x. 1/2 e to the x looks like that. All right. E to the negative x. E to the negative x looks like that. If I multiply by 1/2, it also goes through 1/2 as well. So if I take 1/2 e to the x and add that to 1/2 e to the negative x, what I get is, if I take those and I make it e to the x over 2 plus e to the negative x over 2, I get e to the x plus e to the negative x all over 2. And if you add these points point-wise, 1/2 plus 1/2 will give you 1 there. If you add them all, you'll get a function kind of looks like this. All right, and that is hyperbolic cosine of x. That's what we're going to call it. So we could call it this right here, this e to the x plus e to the negative x. We could say, okay, that's my function, but it's been given the name hyperbolic cosine of x, and I'll tell you why in just a second. All right, now let's take that same graph. Let me erase hyperbolic cosine, and now I'm going to subtract them from each other. So I'm going to take the same pink, and I'm just going to put a minus in between. Minus, minus, minus. So minus and minus, minus e to the negative x. What that one looks like is something different. I'll draw this in a slightly different color, like blue. That one looks like this, right here, something like this. And this one we're going to call hyperbolic sine of x. So that one is hyperbolic sine of x is when you subtract them. It's e to the x minus e to the negative x all over 2. That's this one there. All right, so they're graphed in the book. It's like right here. So here's hyperbolic sine of x right here. Kind of looks like x cubed or tangent, and then hyperbolic cosine of x. Now, why are they called hyperbolic? Well, because they actually lie on a hyperbola whenever we graph them a certain way. So, if you remember from trig, so before I get to this, let me talk about trig for just a second. Sorry, I'm all over the map here. Let's draw a circle. All right, and then we'll draw the xy plane, something like this. And then remember, you have an angle. We'll call that angle T. And then you have an x coordinate and a y coordinate. Then you have one as, let's say it's a unit circle. So you have a cosine of x is cosine of t. Cosine of t is x over 1. So it's the x, and then sine of t is the y. So cosine of t is the x. And sine of t is the y. So any point on that circle is known as cosine t sine t. All right, so we can do the same thing with hyperbolics, actually. Hyperbolics are related with a hyperbola. So any point on the graph is hyperbolic cosine of t, comma, hyperbolic sine of t. So I'm not going to go too much into why that works or whatever, but what I can say is if you take these two guys right here, if you take them, all right, and you do this hyperbolic cosine squared of x minus hyperbolic sine squared of I'm sorry, t. Well, you can say x. X is fine. You get 1. And so, I'm sorry, let's make that a t. I'm being crazy, sorry. Let's make that a t. If you make x be this one and y be this one, then you're going to get x squared minus y squared equals 1. And that's the hyperbola that is drawn right down here. All right, it's this one. Okay, so hyperbolic tangent is just, so this is hyperbolic tangent of x. This is just hyperbolic sine of x over hyperbolic cosine of x. Now in Cal 2, you're going to see why, another reason why we use trig functions for these, because they're going to be related to sine and cosine actually in kind of a very, very cool way. All right, so with that said, how do you find values of them? Well, there's a hyperbolic key on your calculator if you have a calculator like this. I like the TI 30XA. It's very easy to use. Really recommend it. It's like $9 at Target. So if they say find the hyperbolic sine of 1, let's say, all right, you just hit the hyperbolic key. Well, hit the 1 key, the hyperbolic key, the sine key, and you're done. You got it. Okay, so that's those kinds of problems. Now, they're also going to ask you to prove some formulas. We're not going to get to the derivatives just yet, like these right here. So I'd like you to know how to prove this one. And then proving like this one is a little difficult. If you look at this one here, remember in trig, it's 1 plus tangent squared of x is secant squared of x. Here it's 1 minus. So I invite you to learn how to prove all of these. And if you want to see a video or you want me to write out, particularly that one can be difficult, then I will. Let's get to some problems though that you might see in the homework. So where did I put those? Sorry if I'm making you dizzy. Okay, so I really recommend you know how to prove most of these, especially number 11, number 12, number 10, certainly number 9 is a good one, and probably 15 is good. Don't get too hung up on it. The 17 is good as well, but at least know them. All right, so let's talk about the derivative now. So the derivative of hyperbolics is actually really nice. It's this right here. The derivative of sine is cosine, it's easy, but the derivative of cosine is positive sine. So in trig, the derivative of cosine of x, remember, was negative sine of x. Now it's positive sine. Hyperbolic, okay? Tangent goes to secant squared, just like before. The only thing that's different here, this one was negative before, this one was negative before, but this one was positive in regular old secant. Now it's hyperbolic secant. The derivative of that is negative hyperbolic secant x times hyperbolic tangent of x. I want to prove one of these. Let's prove, how about we prove, oh, not the first one. Okay, so what I'm going to do is I'm going to write down hyperbolic sine of x as it is. I'm going to take the derivative of it. So I'm going to write out what it is. It's e to the x minus e to the negative x all over 2. I'm going to take the derivative of this. All right, so the 1/2 can come out because it's just a constant. So it's e to the x minus e to the negative x prime. All right, and so when we take the derivative of this, it's just a sum rule. The derivative of e to the x is e to the x minus, and now this is e to the negative x. The derivative of e to the u is u prime e to the u. So this becomes negative e to the negative x, which makes it positive. And so what we're going to get is 1/2 e to the x plus e to the negative x, which is just cosine of it, hyperbolic cosine of x. And there you have it. So it'd be nice if you could prove some of those. All right, so let's look at some examples. All right, so here we go. Let me pick a different color that you can actually see. What about this one? About 30. Number 30, it says f of x is e to the x hyperbolic cosine of x. So let me call this h, because this is a product rule. You have the product of e to the x and hyperbolic cosine of x. So the derivative, so then h prime of x will be f prime g plus f g prime. And so we'll get e to the x hyperbolic cosine of x. This is f prime g, and then plus. Now we're going to do f, which is e to the x, and then hyperbolic sine of x, because that's the derivative of hyperbolic cosine. And so we really can't do much else with this. Maybe you can pull out an e to the x, and then you're done with it. So that's your answer. I mean, it doesn't have to be hard. All right, so that's that. Okay, let's try 30. 31's good. 31. So 31 said, say y is hyperbolic tangent of the square root of x. So that's hyperbolic tangent. Anytime you see square root, you're going to want to write it as the 1/2 power. So this is y, so y prime. We're going to use the chain rule here. Chain rule says you take the derivative of the outside, that's secant, hyperbolic secant squared of whatever's inside. All right, you get this, and now once we've taken the derivative of the outside, now we take the derivative of the inside, so that's 1/2 x to the negative 1/2 power. And so we get, let's play around with this, hyperbolic secant squared of the square root of x over 2 square root of x, because this piece here is 1 over 2 times 1 over x to the 1/2 power, which ends up being 1 over 2 square root of x. And so there it is right there. Okay, don't cancel these, please. Please don't cancel those. It doesn't cancel because hyperbolic secant squared is of that. Okay, that wouldn't make any sense if you did that. All right, I want to look at one with maybe a natural log. Make sure you understand the difference between these two and get kind of interesting. If you want, I can do a video of that one. Well, heck, I'll just do it real quick and stop the video and do it. We're comparing these two. So this one here on the left is hyperbolic sine of x quantity squared. So when you take the derivative of it, pull the 2 down in front, hyperbolic sine of x, decrease the 2 by 1, and then you take the derivative inside, which is hyperbolic cosine of x. So this ends up being 2 hyperbolic sine of x, hyperbolic cosine of x. We can write as hyperbolic sine of 2x. Think about the formula from Trig, which says sine of 2x is 2 sine cosine. All right, so I think the equivalent is the same in this stuff. Yeah, in fact, it's proven here in number 15. Right. Okay, so now let's look at the other one. The other one's a little different. It's different than this one. When we take the derivative of it, it's the chain rule. So you take the derivative of the outside, hyperbolic cosine of x squared, with that plugged in, and now times the derivative of the inside, which is 2x. So it's just 2x hyperbolic cosine of x squared. Oops, wait. Yeah, that's it, yeah. And we're done. There we go. Now, let's look at this one that says natural log of t and natural log, okay? Let's pull those out. Okay, so these can get interesting. So remember that the natural log of e to the x is just x natural log of e. Oops, that's way too big. All right. But if you have natural log of like e to the x plus e to the negative x or something like that, you cannot distribute this natural log through, okay? You cannot do that. So in other words, natural log of a b, okay, is not natural log of a plus natural log of b. Okay, you can't do that. You can, but it's wrong. It only works for 1 and 0, maybe. All right, so let's get rid of that. So what we can do, though, is when we take the derivative of 34, so it's f prime of t. Okay, so remember, natural log of u, when you take the derivative of it, it's u prime over u. So we'll take the derivative of the inside, which is hyperbolic cosine of t. over, and then sine of t, hyperbolic sine of t. And then this is hyperbolic cotangent of t. I think that was one of the rules, right? Let's go back and review this. Yes, there it is. All right, so now we're going to look at the other one real quick. So all this rule, sorry you're getting dizzy. Let's look at 35 now. So 35 says is now we're going to do g prime of t. G prime of t is, okay, now this is a chain rule. So we take the derivative of the outside, hyperbolic cosine of whatever is inside, and now we take the derivative of the inside, which is 1 over t, natural log of u is u prime over u, and when u is just a variable, it's not a function itself, then it's just 1 over t. All right, and so we get hyperbolic cosine of natural log of t all over t. Now, I wonder what we can do with this. Now, hyperbolic cosine, in fact, I wonder what we could have done at the beginning of the other one. No, now this one here is a little different because hyperbolic cosine of natural log of t, in fact, we probably could have done this from the beginning. This is, okay, so remember what hyperbolic cosine of x is. It's e to the x plus e to the negative x over 2. So wherever there's an x, I'm going to put natural log of t. All right, so here we go. So this is going to be e to the natural log of t plus e to the negative natural log of t all over 2, all over 2. So I'm going to pull out that 2 as a 1/2. And let's play around with this. E to the natural log of t is just t, because remember from algebra, e to the natural log of x is just x. All right, so plus, now I'm going to use a power rule here, pull that negative in front there, and so it'll be plus e to the natural log of t to the negative 1 power. Well, e to the natural log of anything is just itself, and so we get t to the negative 1 there, and then that's times 1/2. And so when you simplify this, you get 1/2 t plus 1 over t, and when you do the math on that, you get 1/2 times t squared plus 1 over t. All right, so we don't want to forget, so it's over t, but we don't want to forget the t that was up here. So we're going to pull that one down, and so we get 1/2 times t squared plus 1 over t squared, because we're taking this fraction here, we're dividing it by t. So you go t squared plus 1 over t, and you divide by t. When you have a fraction over a denominator, you just combine the denominators. So a over b over c is a over bc. All right, and so now this becomes just that, and let me erase all this. So then we get 1/2 times 1 plus 1 over t squared, or however you want to. I'd take this. This is fine. And that's it.